So now that you have reviewed and practiced antiderivatives, we want to talk more about this constant of integration that we have been using, the plus c. And what we're going to do today is find out the actual value of that plus c. Just review how we do that so that we can distinguish one differential equation solution from another one. So when we look at derivatives, we find out that we've got what's called a function family. So if the function is f, then f prime is the derivative of x cubed, which is 3x squared, and the derivative of 7, which is 0. And then the derivative of g prime is 3x squared minus 0. And the derivative of h is 3x squared, and the derivative of pi is 0. So all of these are what we call our plus c values. But they all came from very different derivatives. They all came from the 7 and the negative 5 and the pi. So how can we know exactly what the plus c value is so that we can distinguish this one solution from another? If you just write plus c, how do you know what it is? And so, again, we've got our given function is dy dx. You're usually given the derivative. The antiderivative then is your y plus that constant c. So we only need one single point, okay? And that point would be an x, comma, and a y. So one x, y point to be able to find the particular value of c. Rather than keep it general, we can find a specific value. This is often called the initial value, or sometimes they call it the initial condition. It's the starting point. Okay, it's what you start with initially, and that can be used to find the value of the plus c. So here is a differential equation where we're given the derivative, but we're also given an initial value for the function, starting at the value of 0 for x and 3 for y. So let's see if we can solve this particular solution. So f prime will go to regular f, and then the antiderivatives, so 2x will go to x squared, and then the antiderivative of sine is negative cosine on the outside, and then divided by the chain rule on the inside. And then we have plus our constant of c. And so what that means is that f of 0, which means plug 0 in everywhere, so 0 squared minus the cosine of 2 times 0 over 2 plus c is supposed to equal 3. And so we can solve for c. So 0 squared, of course, is 0. Cosine of 0 is 1, so we have negative 1/2 plus c equals 3. So if we add 1/2 to both sides, we get that c is 3.5, or 7 over 2. So that gives us what's called a particular solution, so that f of x, the particular solution, is x squared minus cos of 2x over 2, or I can put 1/2 of cos of 2x, plus the particular value of 7 over 2. That's called a particular solution. When it's a plus c, it's called a general solution. When it's got plus 7/2, that's called a particular solution. Okay, so given the initial condition that y equals negative 4 when x is 0, find all the functions for y that would satisfy the differential equation dy over dx equals this. All right, so if we have dy over dx, then we know our equation is going to start with y equals. And the antiderivative of 3x squared is 3x cubed divided by 3. And then the antiderivative of cosine x is sine x, and then plus our c value. And we know that the initial condition is that y is negative 4 when x is 0. So that would be 3 times 0 cubed over 3 plus the sine of 0 plus c. So we know that this is 0 and the sine of 0 is 0, so C turns out to be -4. And so the particular solution is that y equals x cubed when I reduce, plus the sine of x, minus the constant value of 4. Okay, here's another one that's given to us as df dt, so a chance for us to watch our variables here. So we're going to have the antiderivative of that be f, but then all of the solution, the antiderivative, would be expressed in terms of t. So let's look at 1 over t, and we talked about that yesterday. That single variable of t, that single power, is going to be an automatic natural log. So that'll be the natural log of the absolute value of t, minus, now the next one is not a natural log because it does not have a single power of t. It has a squared power of t. So you want to think of that probably as t to the -2. So then you can add 1 to that power. So we'll have t to the -1 divided by -1 plus 6t plus c. So now we want to solve that f of 1 equals 0. So that means I plug 1 into the natural log. I'll plug 1 into the other expression. So I've got a double negative here. That'll be a positive. And then this would be 1 over t. But right now we know that t is 1, so 1 over 1. Plus 6 times 1 plus c, and that's supposed to turn out to be equal to 0. So that helps us to figure out what our c value is. Now the natural log of 1 is 0, and 1 over 1 plus 6 plus c equals 0. So c turns out to be -7. So the particular solution to this equation would be the natural log of t, absolute value, plus the fraction 1 over t, plus 6t, and then minus the value of 7. All right, this is our last one. So we're going to find our particular solution, and we're given the differential equation dy over dx. So my equation would start with y, and the rest of my antiderivative would be in terms of x. So e to the 2x. E to the 2x starts out as e to the 2x, and then it is divided by the natural log of e, and then also divided by the chain rule of 2. Minus, and the antiderivative of 3x would be 3x to the second divided by 2, and then we have our constant c. So we can clean this up a little bit. We know the natural log of e is 1, so it might look nicer if we wrote this as y equals 1/2 e to the 2x minus 3/2 x squared plus c. Now this time we're given our initial condition in terms of what the graph is doing. So it says the graph passes through the point, and there's our x and our y values, 1 and 1/2. So 1 goes in for x and 1/2 goes in for y. So 1/2 for y. 1 goes in for x, so 2 times 1, minus 3/2, we have 1, plus c. So let's see if we can solve that here. So that gives me 1/2 equals 1/2 e squared minus 3/2 plus c. So let's add 3/2 to both sides. That gives me 2 equals 1/2 e squared plus c. Now we'll subtract 1/2 e squared. So c is 2 minus 1/2 e squared. So our overall particular solution is 1/2 e to the 2x minus 3/2 x squared, and then the constant was plus 2 minus 1/2 e squared, and that is the particular solution for this differential equation. Okay, so that should be enough for you to work on finding and solving for plus C's on your homework tonight. And then we'll come back tomorrow and we're going to learn something brand new. So we'll be done reviewing, and on Wednesday we'll talk about a new strategy for antiderivatives. Okay, I look forward to seeing you Thursday. I guess it's Thursday, not Wednesday. We'll see you Thursday morning.